At the highest level, mathematics identifies several distinct structures in the decimal system: the Lo Shu magic square, the three-digit Kaprekar attractor 495, the perfect number 496, and repunits like 111 and 1111. These objects originate in disparate branches of number theory. Lo Shu is an ancient additive matrix. 496 is defined by its divisors. 495 is the terminal point of a digit sorting map. Standard analysis often classifies the overlaps between these constants as base 10 coincidences rather than evidence of a shared arithmetic law. Instead, this new synthesis focuses on operator structure, the underlying procedural logic used to generate or reduce these specific values. Under this precise framework, we treat these equations as physical procedures that strip away peripheral details to preserve a fundamental, lower-dimensional core. By treating base 10 digits as physical geometric structures, we can observe how these disparate constants are linked by a shared process of skeletonization. This is the standard 3x3 Lo Shu square. Its primary property is that every row, column, and diagonal sums to the magic constant 15. The magic sum is 15, and the entire grid is balanced around the center coordinate of 5. We apply the first skeletonizing operator, corner removal. This operation discards the even numbers 4, 2, 8, and 6 from the periphery of the grid. The remaining digits 1, 3, 5, 7, and 9 form an axial cross. This subset serves as the geometric spine of the square, anchored at the center value of 5. This reduction discards the square's standard additive properties to reveal its internal axial symmetry. This formula represents the three-digit Kaprekar map. The process requires sorting the digits of a number in descending and ascending order and then subtracting them. In the algebraic expansion, the middle digit, the 10D term, is cancelled out completely during the subtraction. Because the middle digit vanishes, the map's output depends entirely on the outer digits. The equation simplifies to 99 times the difference between the largest and smallest digits. We define this difference as the digit spread, labeled as G. This means the Kaprekar map is a one-dimensional spread process, expressed in decimal form, rather than a three-dimensional digit process. Any three-digit input with non-identical digits contracts until the spread stabilizes at a fixed point of 5. Because 99 times 5 is 495, every valid three-digit number is pulled toward this specific attractor. The Kaprekar operator mirrors the Lo Shu reduction by discarding peripheral digit data to expose a system anchored by the number 5. The number 496 is traditionally studied as a perfect number, meaning the sum of its proper divisors equals the number itself. It is also the 31st triangular number. 31 is the sum of twice the Lo Shu magic sum of 15 plus 1. To see the hinge between these systems, we apply the Kaprekar operator to 496. The digits are rearranged into 964 and 469. We focus exclusively on the extremal digits of the set. 496 has an outer digit spread of 9-4, which is exactly 5. Since the spread is 5, the Kaprekar map results in 495. Because its spread is already at the fixed point, 496 collapses into the Kaprekar attractor in a single step. 496 is the perfect number whose outer digit geometry is perfectly calibrated to collapse into the Kaprekar attractor. We can also treat decimal repunits, like 111 and 1111, as active geometric operators. In a no-carry regime, adding the repunit 111 to 618 adds 1 to every digit position, yielding 729. This process acts as a decimal shell lift, adding a uniform layer to the number. Subtracting the repunit removes that layer. We define the resulting number as a decimal shadow. This mechanism explains why adding the four-digit shell 1111 to 0618 results in 1729. Repunits provide a canonical mechanism for adding or removing uniform boundary layers in base 10 while preserving the underlying digit relationships. These three procedures, extraction, spread reduction, and shell layering, share a common structural language. The novelty of this framework is the synthesis of these distinct procedures into a single category of skeletonizing operators. We must define the boundaries of this interpretation clearly. This framework does not suggest that every related number belongs to a universal doctrine, nor does it elevate 496 to an invariant of magic squares. Instead, it offers a shift in perspective, viewing arithmetic as the physical action of shedding boundaries to find a central spine. Our base 10 system contains a structural topology that is often overlooked when we focus only on numerical values. The one-step collapse of the perfect number 496 into the Kaprekar attractor 495 serves as an intersection where divisor theory and digit spread dynamics meet. By applying axial reduction, we find that ancient matrices, numerical attractors, and divisor logic are all part of a unified geometric landscape.